So today we're going to take a look at the Lewis relationship and how it relates heat and mass transfer. So the first thing that we're going to do here is look at the different equations for heat and mass transfer. So we have heat transfer at a point x is equal to the negative thermal conductivity times the change in temperature with respect to position. And we have the convective heat transfer is equal to the heat transfer coefficient H times the temperature at the surface of an object minus the temperature far away from that surface of the object. Now looking at mass transfer, we know that the molar diffusive flux is equal to the negative diffusion coefficient dAp times the change in concentration with respect to position. We also know that the molar flux is equal to the mass transfer coefficient Kc times the molar concentration at the surface minus the molar concentration far away from that surface. So when we're looking at these equations, we can see that they are very analogous. We have some thermal conductivity, and then some mass diffusivity coefficient, and then we have the heat transfer coefficient, mass transfer coefficient, difference in temperature, difference in concentration, and then some molar concentration gradient and some thermal concentration gradient. So these are very similar equations, and they can be related even further by exploring the driving forces of these top two equations in terms of concentration. So for the heat transfer, when we divide that by when we divide the heat transfer coefficient by the volumetric heat capacity, we get the driving force for heat transfer in terms of thermal concentration. So negative K over rho Cp, which is the volumetric heat capacity, which is density times heat capacity, change in temperature and volumetric heat capacity with respect to position. And then for the molar diffusive flux, this is already in terms of concentration, so it can be left the same. The molar diffusive flux is equal to negative dAb times the change in concentration with respect to position. And then we can also look at momentum, because it also relates to this equation. So we have momentum at a point is equal to the negative viscosity times the change in velocity with respect to position. And then we can get this in terms of momentum concentration when we divide this whole thing by the density. So we get negative u over density is equal to the change in velocity with respect to position times the density. And this is also called the kinematic viscosity. So mu rho is equal to the kinematic viscosity. So we can also determine through experimental data that the Nusselt and Sherwood relations are very similar. So we have the Nusselt number is equal to a coefficient A times the Reynolds number to some power B times the Prandtl number to some power C. Now we know that the Nusselt number is equal to the heat transfer coefficient times some characteristic length d all over the thermal conductivity K. We also know that the Sherwood number is equal to some coefficient A times the Reynolds number to some power B times the Prandtl number to some power C. And this is equal to the mass transfer coefficient times some characteristic length d all over all over the diffusion coefficient dAB. So through experimental data, we find that all of these coefficients for both the Nusselt and the Sherwood number are the same. So A is the same for both the Nusselt and Sherwood number, B is the same, C is the same. So we can divide these two equations and relate the Nusselt and the Sherwood number to get a mass and heat transfer relationship. So we have the Nusselt and Sherwood number, Nusselt over Sherwood is equal to A Reynolds number, B cancels out, and we have, this should be the Schmidt number at the bottom. For the Sherwood number, the Schmidt number is to the C power. Is equal to the Prandtl number over the Schmidt number to the C power. So this is interesting because we know that the Schmidt number over the Prandtl number is equal to the Lewis number. So the Nusselt over the Sherwood number is equal to 1 over the Lewis number to the C power. So for moist air, which is what we're going to be talking about in this exam, because we're going to be talking about wet bulb temperature and adiabatic saturation temperature, moist air has a Lewis number of approximately 1. So we can simplify this equation just by using the 1 over Lewis number as 1. So the C power can cancel out, and we get the Nusselt over the Sherwood number is equal to the Prandtl number over the Schmidt number. So when we divide these two equations, the Nusselt number and the Sherwood number, the characteristic length D cancels out, and we get the heat transfer coefficient H times the diffusion coefficient dAB over the mass transfer coefficient Kc times the thermal diffusivity is equal to the Prandtl number over the Schmidt number. Now, we know that the Prandtl number is equal to the kinematic viscosity over alpha, which is the thermal diffusivity, which is this value right here, negative K over Cp. This is alpha, which is the thermal diffusivity. And then the Schmidt number is equal to the kinematic viscosity over the diffusion coefficient dAB. So we can set these two halves of the equation equal to each other, so we get heat transfer coefficient times the diffusion coefficient all over mass transfer coefficient times the thermal conductivity is equal to the kinematic viscosity over alpha all over the kinematic viscosity times the diffusion coefficient dAB. Now we can simplify this a little bit. The diffusion coefficients cancel out, and the kinematic viscosity terms cancel out, and we get H over Kc times the thermal conductivity is equal to 1 over alpha. So up here, alpha is equal to the thermal conductivity divided by the volumetric heat capacity. So we have H over Kc times K is equal to 1 over K over rho Cp. So the thermal conductivities cancel out, and we get that. So this is very significant because we have the volumetric heat capacity, which is a known quantity, which relates to the ratio of the heat transfer coefficient and the mass transfer coefficient. The mass transfer coefficient is very hard to come by because the experiments to find it are very, very difficult, but the heat transfer coefficient is much easier to find through heat transfer experiments. So we can easily find the mass transfer coefficient by finding the heat transfer coefficient and relating it to the volumetric heat capacity. So now that we've established the Lewis relation, we can create an energy balance and then use the Lewis relation to solve for the pressure of water vapor in the air at a dry bulb thermometer point in order to determine the relative humidity of the air. So the first thing we need to do is to do an energy balance. And we know that the rate of enthalpy loss from the wet bulb thermometer is equal to the heat transfer from the air far away from the wet bulb thermometer to the surface of the wet bulb thermometer. So we can write this as the enthalpy, the latent heat of vaporization times the mass transfer coefficient Kc times the difference in concentration first at the surface of the wet bulb thermometer minus the concentration of water vapor far away from the wet bulb thermometer, all multiplied by the molecular weight. Since we have molar concentrations here and we have a mass transfer coefficient here, we need to convert this to mass concentration through molecular weight. So this is the rate of enthalpy loss from the wet bulb thermometer, and this is equal to the heat transfer from the air far away from the wet bulb thermometer to the surface of the wet bulb thermometer. So the Lewis relationship that we established in the last part of the exam was the heat transfer coefficient over the mass transfer coefficient, Kc, is equal to the volumetric heat capacity, rho Cp. So we see on this side of the equation we have the mass transfer coefficient, and on this side we have the heat transfer coefficient. So we can divide each side of the equation by the mass transfer coefficient, and then use the Lewis relationship to sub in the volumetric heat capacity. So we divide each side by Kc, and we get the latent heat of vaporization times the concentration difference times the molecular weight is equal to the volumetric heat capacity, rho Cp, times the difference in temperature from the dry bulb and wet bulb. So now that we have this, we have everything in terms of the volumetric heat capacity. We can use the partial pressures to find the relative humidity. So the molecular rate and latent heat of vaporization stay the same, but we can convert partial pressures into, we can convert the concentration into partial pressures. So at the surface of the wet bulb thermometer, the pressure of the water vapor is the saturation pressure of the water vapor. So we have the saturation pressure of the water vapor at the surface at the temperature of the water, and that is divided by RT. So this is the concentration in terms of partial pressure. And then far away from the surface, we have the pressure of the water vapor far away from the surface. So that is just the pressure of the water vapor far away from the surface, again divided by the ideal gas quantity times the temperature in order to get the concentration. And then on this side, we can convert density in terms of pressure as well. So we have the total pressure of the air and water mixture times the molecular weight, the average molecular weight of the air and water mixture far away from the surface, again divided by the ideal gas constant times the temperature. Now these temperatures can be anything. Since they're in Kelvin, the difference in temperature isn't significant enough to make a huge difference in the values that you get out of this. And then this is again multiplied by the heat capacity, and then the difference in temperature from the wet and dry bulb thermometers. So now that we have this, the RTs cancel out, and we can rewrite this equation for the last time. We have the molecular weight times latent heat of vaporization times the saturation pressure of the water vapor at the temperature of the water minus the partial pressure of the water vapor far away from the surface of the wet bulb thermometer. And this is equal to the total pressure times the average molecular weight of the air and water mixture times the heat capacity, and then the difference in temperatures from the dry and wet bulb thermometers. So now that we have this, we can take a look at the values that we already know. So we know the total pressure of the air and water mixture. We know the average molecular weight of the air and water mixture. We can find the heat capacity on the table. We have the dry bulb thermometer reading and the wet bulb thermometer reading. We know the molecular weight and the rate heat of vaporization. And we can calculate the saturation pressure of the water using the A1 equation. So the only thing that we do not have is the pressure of the water far away from the surface at the dry bulb thermometer. So we can solve for this by plugging in all these values for this equation, and then the relative humidity, which is what we're looking for in this problem, is just a ratio of the partial pressure of the water vapor at the dry bulb thermometer point divided by the saturation pressure of the water vapor at the surface. So by calculating the partial pressure of the water far away from the surface, we can determine the relative humidity by dividing it by the saturation pressure of the water, which can be determined by the A1 equation. So for this part of the exam, we want to establish a relationship between the wet bulb thermometer temperature equation, which we explored in the last portion of the exam, to the adiabatic saturation temperature equation, which we will establish in this portion of the exam through another energy balance. So rewriting the equation from the last portion of the exam, we have the latent heat of vaporization times the molecular weight times the difference of partial pressure of the saturated water vapor, saturated air and water vapor at the temperature of the water, minus the partial pressure of the water vapor far away from the surface of the wet bulb thermometer, is equal to the total pressure of the air and water mixture times the average molecular weight of the air and water mixture, times the heat capacity, times the difference of the temperature of the dry bulb thermometer minus the temperature of the wet bulb thermometer. So when establishing, so this is for the wet bulb thermometer temperature, and when establishing the adiabatic saturation temperature equation, we can consider an infinitely long pipe that is perfectly insulated. Water is continuously flowed through the pipe, and the water remains the same temperature throughout. So we have, and then air is blown across the top, so we have the mass flow rate of the air and temperature going into the tube, and this is the temperature of the water, and then out here we have the temperature going out of the air and the partial pressure of the water vapor going into the tube and the pressure of the water vapor coming out of the tube, and then the mass flow rate of the air will remain the same throughout. So we can establish, and we know that coming out of the tube, the partial pressure of the air will just be equal to the saturation pressure of the air at the temperature of the water, because the air will be fully saturated at that point. So now that we have drawn this diagram, we can do an energy balance for the enthalpy in and the enthalpy out of this scenario. And for the enthalpy out and enthalpy in, there's two main contributions. The first is the heat of vaporization, and the second is the heat transfer of the water and air. So for the enthalpy in, we're going to do the rate of enthalpy in. So we have m dot of the air, which will give us the mass flow rate of the air. And then the first contribution is the heat of vaporization. So we have the latent heat of vaporization times, we want to multiply this by the mass concentration of the water in the air at this point. So we can solve this by saying the partial pressure, or the pressure of the water vapor, P1, divided by the ideal gas equation times the temperature. And we want to multiply this by the molecular weight, since we have the mass flow rate, not the molar flow rate. And then to get a partial pressure, we need to multiply this by the reciprocal, the total pressure. So we have the ideal gas equation times the temperature divided by the total pressure times the average molecular weight. And this will give us the partial pressure of the water vapor going into the pipe. And then we want to do the second part of the contribution to enthalpy, which is the heat transfer. So we have the heat capacity of the air times the temperature of the air going into the tube. Okay, and then for the enthalpy out, it will be very similar, but just using the terms for the air going out and the partial pressure of the water going out. So we have, again, the mass flow rate of the air, since this will remain the same, and then heat of vaporization, and then instead of the pressure of the water coming out or going in, we'll have the partial pressure of the water going out times the molecular weight divided by the ideal gas constant times the temperature, and then again the same, the ideal gas constant times the temperature divided by the total pressure times the average molecular weight, and we want to multiply this, or add the heat capacity times the temperature of the air coming out in this situation. So we can set the enthalpy in equal to the enthalpy out, and then cancel out a couple of things. So the mass flow rate is the same going in and going out, so we can cancel that out. And we can bring each side of the equation toward, or move the different terms to different sides of the equation in order to factor out some of these. So for example, the ideal gas constant times the temperature cancel out in both of these. And we can factor out the latent heat of vaporization, the molecular weight, the total pressure, and the average molecular weight. If we bring over that to the equation to this side, so we have latent heat of vaporization times the molecular weight divided by the total pressure times the average molecular weight, and then we have P1 minus P2. And we can do the same for the heat capacity and temperature by bringing this over to this side of the equation. So we have heat capacity times the temperature going out minus the temperature going in. So if we look at this equation, we can see that it is almost identical to the equation that we established in the previous portion of this exam. If we divide everything by the total pressure and the average molecular weight, we get almost the same equation, except for this is in terms of the wet bulb thermometer and dry bulb thermometer readings. We can see that these are flipped, both of these are flipped, but if we negate this equation, they're very analogous to the terms down here. So we have the partial pressure of the water as far away from the wet bulb thermometer is analogous to the pressure of the water going, or the pressure of the water vapor going into the tube. We also have the pressure of the water saturated on the wet bulb thermometer is analogous to the partial pressure of water coming out of the partial pressure of water vapor coming out of the tube which is the saturated water pressure. And then over here, T2 is analogous to the saturation temperature of the water, which is wet bulb thermometer reading, and T1 would be analogous to the dry bulb thermometer reading. So through these equations and relating them, we can see that the adiabatic saturation temperature is the same as the wet bulb thermometer reading.